What if the ground beneath a quiet stretch of Oregon desert was not actually opening, but simply revealing a wound that formed thousands of years ago, then froze in place like a geological photograph? What if the dramatic 2-mile line etched into the sagebrush was not a warning of the Earth tearing apart today, but instead a leftover scar from an ancient moment of stress buried deep in volcanic rock? And most importantly, how do scientists distinguish between a crack that is alive and growing and one that only looks like it might be? These questions sit at the center of a growing wave of online attention surrounding a feature in Central Oregon known as crack in the ground. The name alone invites imagination. A 2-mile-long opening, or about 3.2 kilometers in length, cutting through basalt plains north of Christmas Valley, looks at first glance like something actively ripping apart the crust. Photos emphasize shadowed walls dropping into narrow passages, sometimes up to 70 feet, around 21 meters deep. In a world where satellite images and viral posts often frame geology as sudden catastrophe, it is easy to see why claims of an expanding fissure spread quickly. But when geologists step into the same landscape, the story that emerges is slower, more mechanical, and far less cinematic. The crack is not opening in real time. It is not propagating like a tear in fabric. It is not behaving like the active rifts of Iceland or East Africa. Instead, it is a preserved surface fracture formed in a very specific tectonic and volcanic environment long ago, likely more than 14,000 years in the past, during the final pulses of volcanism in the region. What is visible today is the uppermost expression of deeper crustal deformation, locked in place by dry climate and geological timing rather than ongoing tectonic force. To understand why this distinction matters, it is necessary to move away from the surface appearance and into the architecture of the crust beneath Central Oregon. The crack sits within the high lava plains, a volcanic province built from repeated basaltic eruptions and slow extensional stretching of the North American crust. This is not a single fault line snapping open, but a broad zone where the lithosphere is being pulled apart in a distributed way. In geologic terms, this is extension, a process where the crust is gradually stretched, thinned, and broken along numerous small normal faults, rather than one dominant fracture. The rocks that host crack in the ground tell part of this story directly. Much of the surface is made of basalt flows, solidified lava that once moved like a dense, glowing fluid across a relatively flat landscape. One of the oldest key volcanic events in the area occurred roughly 740,000 years ago, when the Green Mountain Shield volcano produced extensive basalt flows that blanketed the region. These flows cooled into thick, rigid layers. Much later, around 14,000 years ago, eruptions from the Four Craters volcanic field sent newer basalt across parts of the same terrain. These two volcanic episodes form a kind of geological bracket. Any structure that is cut by the younger flows must be older than them, and anything that cuts the older flows but is buried by the younger ones must have formed in between. Crack in the ground fits precisely into that window. It exists below or within the younger lava coverage in some areas and above older lava in others, indicating it formed after the older Green Mountain flows had already hardened, but before the youngest Four Craters lava fully sealed the landscape. This places its origin near the end of the last ice age, a time when regional stress changes in the crust coincided with renewed volcanic activity. However, and this is where misunderstanding often begins, crack in the ground is not itself a volcanic fissure. It is not a vent. It is not a place where magma erupted or gas forced the ground apart. Instead, it is a tensile surface fracture formed in response to movement on a deeper buried fault. That distinction separates it from active rift cracks elsewhere in the world. Beneath the visible chasm lies a normal fault, part of a broader extensional system. In a normal fault, the crust is being pulled apart so that one block drops downward relative to another. In this case, the northeast side of the buried fault subsided by roughly 30 feet, about 9 meters, relative to the southwest side. But instead of producing a sharp, exposed fault scarp at the surface, the thick basalt layers above did something more subtle. They bent. This bending is critical. Basalt, once cooled, is strong but brittle. When it is forced to drape over a slowly sinking block, it does not always break cleanly at the fault plane. Instead, it can flex like a rigid board being gently warped. The result in this Oregon landscape was a monocline, a broad fold where layers tilt downward without immediately breaking at the surface. But as the bending increased, the outer surface of the lava cap experienced tension. Just as the top of a bent beam stretches while the bottom compresses, the upper crustal layers were pulled apart. Eventually, the tensile stress exceeded the strength of the basalt surface. The rock did not fail along the deep fault, but at the top, where it was weakest under tension. The result was a shallow, linear fracture directly above the bending zone. This is crack in the ground. Geologists describe this as a tension mode fracture, meaning the rock is pulled apart rather than sheared sideways. Importantly, this fracture affects only the uppermost layers of lava, not the full thickness of the crust. Beneath it, the fault remains a tightly closed shear structure, extending deep into the upper crust. As one geological synthesis by David Sherrod and colleagues has emphasized, the visible crack and the buried fault are mechanically related but not the same thing. One is deep and closed, the other is shallow and open. This layered relationship explains why the crack can appear so dramatic at the surface while remaining geologically limited in scope. The surface expression is essentially a tear in a brittle cap sitting above a much broader, more distributed deformation zone. Once formed, the crack did not behave like an actively spreading rift. That is one of the most important points clarified by modern field studies and remote sensing data. There is no measurable global positioning system signal indicating that the two sides of the crack are moving apart today. There is no seismic catalog showing persistent small earthquakes tracking its growth. There is no deformation field comparable to known active spreading centers. In contrast, active rift environments such as Iceland or the East African Rift show continuous, measurable extension rates. In Iceland, for example, plate divergence can reach about 20 millimeters per year, roughly 0.8 inches per year. That kind of movement produces frequent earthquakes, repeated fissuring, and observable year-to-year changes in surface cracks. Nothing like that has been observed in Central Oregon at this site. Instead, what field observations show is the opposite tendency over long timescales. The walls of the crack slowly degrade. Rockfalls accumulate at the base. Wind-driven sediment enters from above. In many places, the fissure is partially narrowed by collapse blocks or infilled by sand. The reason it still looks open is not because it is actively widening, but because the region is dry enough that erosion and sedimentation are slow. The arid environment preserves the shape rather than refreshing it. This preservation effect is often misunderstood. A landscape that remains sharply visible is not necessarily active. It may simply be stable enough that nothing is erasing it. The broader tectonic setting adds another layer of complexity. Central Oregon lies near the transition between stable continental crust and the more actively extending basin and range province. The region is not uniformly stretching like a single rubber sheet. Instead, it is deforming in patches with small normal faults distributed across volcanic terrain. Some of these faults show evidence of prehistoric earthquakes, possibly reaching magnitudes near 7 or greater, but such events are extremely infrequent on human timescales. The geological record suggests that deformation here happens in pulses rather than continuous motion. Stress builds slowly over thousands of years, then releases in occasional large earthquakes. Between these events, the crust may appear almost motionless. This episodic behavior is crucial to understanding why crack in the ground should not be interpreted as an active warning signal. The fault system beneath it is not dead in a tectonic sense, but it is currently not expressing measurable surface movement at this location. The crack is essentially a frozen snapshot of one past episode of deformation, preserved by timing and climate. Another key factor is lava loading. When large volumes of basalt erupt and spread across a region, they add significant weight to the crust. This can cause flexure, bending the crust downward under the load. In Central Oregon, repeated lava flows from volcanic fields such as Four Craters contributed to uneven loading of the crust. This loading can enhance stress along pre-existing faults, encouraging flexure and tensile cracking in overlying layers. In this model, Crack in the ground is not the product of a single clean fault rupture but a combined response. Regional extension, pulling the crust apart, local fault movement dropping one block, and volcanic loading bending the overlying basalt until it fractured at the surface. The crack is therefore a composite structure formed at the intersection of tectonics and volcanism. This complexity is what makes it scientifically interesting and visually misleading at the same time. The eye sees a clean cut. The geology reveals a layered sequence of bending, loading, and brittle failure distributed over depth. The question that naturally follows is whether this structure could reopen or widen again. Based on current geophysical evidence, there is no indication that it is actively doing so. No modern instruments detect progressive widening. No deformation networks show differential motion across its length. The most likely future behavior is not expansion but gradual degradation. If a significant earthquake were to occur on a nearby fault segment, the response of the crack would depend on shaking intensity and ground stability. Rather than pulling apart further, the more probable outcome would be partial collapse of the walls. Blocks from the edges could fall inward, reducing the apparent openness of the fissure. Over time, repeated seismic shaking combined with gravity and weathering would tend to obscure the feature rather than enhance it. This is consistent with how similar tensile fractures behave in basaltic terrains worldwide. Open fissures rarely remain open indefinitely unless they are continually reactivated or maintained by active spreading. Without ongoing extension at the surface, gravity and sedimentation dominate. There is also an important temperature and microclimate effect inside the crack. Measurements and field observations indicate that temperatures within the deeper sections can be significantly cooler than the surrounding desert surface, sometimes by about 20 degrees Fahrenheit, approximately 11 degrees Celsius, lower than surface conditions. This cooling is due to trapped cold air and reduced direct solar heating. While this creates a striking hiking experience, it has no tectonic significance. It is simply a consequence of geometry and airflow. What remains striking from a scientific perspective is not that the crack is growing, but that it has survived so well. Many similar surface fractures formed in basalt provinces would normally be erased over thousands of years. They collapse, fill, or become buried. In this case, the combination of arid climate and relatively low recent tectonic disturbance has preserved it almost intact since its formation. The Bureau of Land Management describes it as an ancient fissure that remains nearly as it appeared shortly after formation. That phrasing is important. Nearly as it appeared does not mean unchanged forces are acting on it. It means that the balance of erosion and infill has been slow enough that the original geometry is still readable. In modern geology, that distinction is central. A feature can be visually dramatic without being dynamically active. It can look like a tear still opening while actually being a fossilized record of stress that ended long ago.